We're looking at the 9.7 and 9.10 review worksheet number 4. These are just review items that will be helpful and useful to know. Here's the Taylor rule, the LaGrange error bound, and here are the three most common Maclaurin series that we need to be able to write out and memorize, as well as the general rule that that goes with these Maclaurin series. All right, let's look at number 4 here. Find the power series for the function centered at C, determine the interval of convergence. So what we're trying to do is we have f of x equals 3 over 2x minus 1. This is, but we want this to be centered at c equals 2. But this is also in the form of a geometric series. So if we can somehow get this form to have a 1 minus r and then a coefficient up top and a number, numeric value up top, then we can figure out what the first term is and what the ratio is, and from there we can build not only our power series, but then also use that to help us determine our radius of convergence and also our interval of convergence. So we start off with 3 over 2x minus 1. We know our center is at 2. So if our center is at 2, we have to make that adjustment. So right now, 2x minus 1, this is going to be centered at 0. But to make this centered at 2, we want to have it as 2 parentheses x minus 2. However, if we do x minus 2 inside the parentheses, we are essentially changing the overall value of this expression. So we have to make some adjustments outside so that we maintain balance and maintain the fact that this should be, that we don't want to be changing the value of this expression. So what's happening here is if we included x minus 2 inside the parentheses, then really this from 2x, from initially starting off at 2x, it's now becoming 2x minus 4. So essentially, if we're including a minus 4 in the expression, we have to balance that out with a plus 4 outside, so that this overall denominator is not going to change from 2x minus 1. So 2 parentheses x minus 2 minus 1 plus 4, and that plus 4 is to help cancel out the fact that we're adding a negative 2, which after being distributed will become a negative 4. Okay, so if we combine terms here, we get 3 plus 2x minus 2. So this is getting closer to making it look like our geometric sum, so that we can pull a sub 1 and r. Okay, but we're not quite there yet. Another adjustment we have to make is we need to make sure that the first term in the denominator, that coefficient, that's constant, needs to be a 1, and that needs to be followed by a minus. So right now we have 3 plus, so we have to make that adjustment. So if we want to force this 3 to be a 1, what we can do is we can divide every term by 3, and that way we're not changing the overall equation or expression. So divide everything by 3. If I divide everything by 3, I can cause this portion to be 1. And then I also want to turn this plus to be a minus. But if I want to create a minus sign, I have to make sure I maintain balance and also have a negative somewhere else. So I'm going to make this 1 minus a negative 2/3 x minus 2. So what's happening is we divide every term by 3, and then also we made this a double negative to make this form match, so we can pull a sub 1 and r correctly. So looks like a sub 1 is going to be the 1, and looks like the ratio is going to be negative 2/3 x minus 2 to the nth degree. So we know we have the ratio. Now we have the ratio. This is x. This is essentially absolute value of x minus c is less than r. So here's x minus c is less than r. C is going to be at 2. So we just need to solve for x. If we solve for x, we can locate our ratio as well as our interval of convergence. So first thing, I'm going to multiply by 3 halves to the other side. So multiply by 3 halves, make it x minus c is less than r. So here I see my c value is 2, and then my ratio is 3 halves. So now it's in the form of x minus c minus x minus c is less than r. If I get rid of the absolute value bar, then really it's x minus 2 is sit between negative 3 halves and 3 halves. And if I add 2 to both sides, I'm going to get x is between 1/2 and 7/2. So this is my interval of convergence, and then my ratio is going to be 3/2. Okay. Here's another example here. That this is 4b. We have 4 over 5 minus x, center at c equals -2. So we have to include the fact that this is a -2 center. So I'm going to put make this a negative parentheses x plus 2. And if I do a plus 2 here, that's really a -2. So I have to make sure there's a balance with a 2 out here. So if I clean this up, I get 7 minus parentheses x plus 2. So we're close, getting close to the form that we need to identify our a sub 1 and our ratio, our first term and our ratio. So we need this term to be a 1. So I'm going to divide the 7 by 1 as well as every term by 1. So this becomes 4/7, 7 over 7, 1/7 x plus 2. So this becomes a 1. Okay. And after that becomes a 1, I know this is my ratio and this is my first term here. So this is my general rule. My ratio x minus c is less than r. So I can make this x plus 2 is less than 7. The absolute value of x plus 2 is less than 7 if I multiply both sides by 7 over 1. And then that tells us that the center is -2 and our ratio is 7. So then if we write this as x plus 2 is between 7 and -7, we can subtract 2 to both sides. So we have our interval of convergence between -9 and 5. Okay, number 5. Find the interval of convergence for the power series. We have 3 to the n, x minus 2 to the n over n. So we have the general term. So interval of convergence in general, this is given as a general form. What we can do is we can go through ratio test, right? Since we have the exponent here set up and ready for us. So ratio test tells us we do limit as n approaches infinity for a sub n plus 1 divided by a sub n. Dividing by a sub n is the same thing as multiplying by the reciprocal of a sub n. Okay? So here's a sub n plus 1, replacing every n with n plus 1, multiplied by the reciprocal of a sub n. And then here I'm looking to clean up and cancel out. One of the 3's will cancel out, leaving us, 3 to the n will cancel out, leaving us with 3. X minus 2 n will cancel out, leaving us with x minus 2. We're left with n over n plus 1. Really, we're just evaluating the limit as n approaches infinity for n over n plus 1. And because the degrees of the degrees match, we can just take the leading coefficients, which is 1, and then that leaves us with 3. Absolute value of x minus 2 is less than 1. So here we can divide both sides by 3. So x minus 2 is less than 1/3. Here's our center. Here's our ratio. Here's our radius of convergence. And then, so we know that because x minus 2, absolute value of x minus 2 is less than 1/3, we can also simplify further and say x minus 2 is between 1/3 and -1/3. And then when I add 2 to both sides, 2 minus 1/3 becomes 5/3. 2 plus 1/3 will be 7/3. So my initial interval convergence will be between 5/3 and 7/3, and then we have to test the endpoints. So that's what the bracket and parentheses there, just to help remind us that we need to determine which one to use. Will it be the bracket or parentheses at each of the endpoints? So that means we have to test the endpoints. So we're going to take 5/3 and plug back into our rule of sequence. So plug 5/3 in for x. So 5/3 minus 2 will be -1/3. So -1/3 to the n. We see that if we clean this up a little bit, the 3 to the n, -3 to the n will cancel out, leaving us with -1 over n. And -1 to the n over n, this is essentially alternating harmonic series. So we know that if we have a harmonic series where there is alternating signs, this will be good enough for it to converge. So this will converge by alternating series test. If we then test the other endpoint, which is 7/3, plug 7/3 in for x, 7/3 minus 2 will give us 1/3. And then if we cancel this out, we're left with 1 to the n over n. 1 to the n over n is essentially 1 over n, which is the harmonic series, which we know diverges. So we know that at 7/3, it will be a parentheses. Okay, let's go to the back here. Number 6. Let f be the function given by cosine of 3x plus pi over 6. Let p of x be the 4th degree Taylor polynomial. So we have to build this Taylor polynomial. So with f of x, we have cosine of 3x plus pi over 6. We're going to go through and find each of the derivatives until the 4th derivative. Okay. So the derivative for cosine of u is negative sine of u times u prime. And u prime is going to be 3 because the derivative for 3x is 3, and then pi over 6 is a constant, so it will go to 0. And then the derivative for sine of u is negative cosine of u times u prime. So every time we find a u prime, we're going to multiply to the previous coefficient. So that's why we see that each of these derivatives will keep incrementing by factors of 3. So the derivative for cosine of u is negative sine of u times u prime. So the two negatives cancel out. Sine of u times u prime, 9 times 3 is 27. Sine of u times u prime. Sine of u becomes cosine of u times u prime. And then I also found the 5th derivative. We might need this later. Okay, so we're going to evaluate each of these derivatives at 0. So plug 0 in for x. And for plug in 0, we can evaluate the derivative to give us root 3 over 2. F prime of 0 will be negative 3 halves. F double prime will be negative 3 or negative 9 square root of 3 over 2. I'm going to rewrite it as negative 3 squared root 3 over 2. So we can kind of begin to see some of the pattern that will develop. The third derivative is 27 over 2, or 3 cubed over 2. Next, the 4th derivative, evaluate at 0, plug 0 in for x, and evaluate, we get 81 root 3 over 2, which is 3 to the 4th root 3 over 2. So notice that there is a coefficient that's always incremented by factors of 3, so that's why we get 3 to the 1st, 3 squared, 3 cubed, 3 to the 4th. And then the 5th derivative, which we will need later, is negative 243 over 2 when the 5th derivative is evaluated at 0, and we get negative 3 to the 5th over 2. All right, so we can build our Taylor polynomial. This is going to be our y sub 1 minus our slope times x minus x sub 1, and then we can build starting with the 2nd derivative here, because the first 2 terms is just going to be a tangent line. Okay, so this is the f double prime at 0. Sorry, f double prime at 0, evaluated at 0 over 2 factorial times x minus c to the 2nd power. And then here is the 3rd derivative evaluated at 0 over 3 factorial, x minus 0 cubed. And then the 4th derivative evaluated at 0. And if we clean all this up, we're going to get to our 4th degree Taylor polynomial, okay, provided there. Okay, part B. Use the LaGrange error bound to show that the Taylor polynomial evaluated at 1/6 minus, the original function at 1/6 minus the Taylor polynomial evaluated at 1/6. The difference between the two of them will be will not be off by more than 1 over 3,000. Okay. So LaGrange error bound tells us that we're going to have to find, if we're evaluating the 4th degree polynomial or determining the error for the 4th degree polynomial, we're going to have to work our way down to the 5th derivative. So n is 4, so therefore n plus 1 is 5. The 5th derivative evaluated at z, so we want to try and maximize this value, try to find what is the largest value that this could be, and we want to kind of go through a range of z values to determine what will cause it to be the largest value, so we can create a safe upper bound to determine our maximum error. Over n plus 1 factorial, so divide by 5 factorial, x minus c, so we know that x is going to be 1/6, c is center at 0, and to the 5th. So here we have the 5th derivative evaluated at z over 5 factorial 1/6 minus 0 to the fifth. So what is the largest value that this fifth derivative could be? So here's the fifth derivative, which is negative 243 sine of 3x plus pi over 6. And no matter what the x value is, if we increment this to infinity, this sine of our u value will keep oscillating between -1 and 1. Because it oscillates between -1 and 1, there's nothing that will be greater than 1 ever for this expression with the absolute value of, which means that this 243 is the largest that this expression could be, since either we're multiplying 243 by 1 or multiplying by 243 by a decimal value that is somewhere between -1 and 1. Okay, and those values, absolute value, will be less than 243. So we know 243 is the largest that this expression can be, over 5 factorial times 1/6 to the fifth. And if we clean this up, if we use our calculator, we're going to get 0.002604, which, if we check, is less than 1,000. Okay, part C. Find the value for the 68th derivative evaluated at 0. So rather than having to go through the derivative 68 times to figure out what this value would be, if we look at this, we're going to see that there is a pattern that the derivatives will kind of go through a series of variations, but eventually it's going to go back to the original form. So really it's going to go through 4 iterations, and then it's going to come back to the original form. So so if we know that, then what we can do is we can simply do 68 divided by 4 and figure out which of these variations the 68 derivative will land on, right? It will have to be one of those 4 variations. So the way we look for that variation is we look for the remainder. Okay, so we do 68 divided by 4, and if we work this through, we're going to get 28 with a remainder of 0. So that means 68 derivatives later, it will come back to this form, which is cosine of 3x plus pi over 6. However, because we're going through 68 derivatives, these coefficients will keep increasing by factors of 3. So the third derivative is 3 cubed, fourth derivative is 3 to the fourth. So it makes sense that the 68th derivative will be 3 to the 68th power with this form. So 3 to the 68th power root 3 over 2 should be the 68th derivative evaluated at 0. So 3 to 68th root 3 divided by 2. Right. Now, if we want to find the full coefficient in the Taylor rule would be the 68th derivative evaluated at 0 divided by 68 factorial. But it's only asking for the 68th derivative at 0. It's not asking for the full coefficient. If it was asking for full coefficient, then we have to provide this entire expression here. Okay, this is part B, which is finding the 57th derivative evaluated at 0. So the same idea, rather than having to evaluate the derivative 57 times, we can just do 57 divided by 4 and see which variation this derivative will land on. So if we do 57 divided by 4, we're going to get 14, remainder 1. So remainder 1 will have to be this variation. So this variation will simply be -3 over 2, -3 to whatever power this derivative is. And since we're dealing with the 57th power, it'll be -3 to the 57th power divided by 2.